All right, solid, liquid, gas. Just remember from chapter 6, solids are incompressible. All your molecules of a solid are connected. The molecules will vibrate, but they do not move around. Liquid, these molecules will move around. They will go all over the place, but within the container. Remember, the liquids take the shape of the container. Gases are moving in all directions, banging against the wall, banging against other molecules. All right, and so you can compress a gas. So gases are compressible fluids. Liquids are relatively incompressible. You can compress them a small amount, but relatively incompressible. Solids are almost completely incompressible, and they are rigid. Solids are rigid. Liquids take the shape of the container. Gases are all over the place. If they're in a container, they take the shape of that container as well, if the container is sealed. All right, and so when we change from one state to another, if we heat our solid, it will melt into a liquid. If we heat our liquid, it will vaporize into a gas. All right, and so when you're going, and then of course, if you had like dry ice and you heat that, all right, it would then turn right to a gas. So everything here going to the right is endothermic. It requires heat in order to melt and to vaporize and to do sublimation. All right, and so you need to know that when you go from a solid to a liquid, it's called melting, or everyone knows that, but you also have to know that that is called fusion. Heat of fusion is the heat of melting. And then, of course, liquid to gas, most of you know that's called vaporization. So liquid to gas vaporization. All right, and so then the other direction, you have your condensation when the gas goes down to a liquid. So you have condensation. I don't use liquefaction, but it's also called liquefaction. I will call this always condensation. When you go from a liquid to a solid, everyone knows that that is freezing. All right, and so when you go from a gas down to a solid, this is called deposition. All right, and so these are all exothermic. So everything going to the left here is exothermic. It will release heat. Everything going to the forward direction requires heat. All right, so then we're going to talk about a vapor pressure. So when you put a liquid into a container, that liquid is going to evaporate. All right, but if this container has a plug, so it's sealed at the top, all right, so then the vapor cannot escape. So it is then into your flask. And so the vapor that is above your liquid is called the vapor pressure. Now, once you hit a certain vapor pressure at a given temperature, it is then at equilibrium. All right, and so in A, there's no vapor pressure, there's no liquid molecules in the gas phase. So here they're showing that a few have now reached the gas phase. And now they're showing more is in the gas phase. And so in part C here, they have reached an equilibrium. And so that means that for every one molecule that goes from the gas to the liquid, one molecule goes from the liquid to the gas. So it stays at a constant vapor pressure at that temperature. Of course, if you heat it, you're going to raise the temperature, you're going to raise the vapor pressure. And if the pressure gets too high, it will blow the cork off the top. All right, so here's a bunch of different liquids, and you heat them up. And so you see when you're going here in temperature, you're increasing the temperature. And here you see that as you increase the temperature, you increase the vapor pressure. All right, and so then you have your 760. That one is important because that's 1 atmosphere. That is normal pressure. All right, so when you hear the word normal, that means 1 atmosphere or 760 millimeters of mercury. And so you would have the boiling point of here diethyl ether, and here your chloroform, and here your carbon tetrachloride, and here your water. We know the boiling point of water. it is 100. All right, and so that's what the boiling point of water is, 100. If you wanted to know the boiling point of carbon tetrachloride, well, then you would come down here and see that, well, it's about 70, I don't know, 4. You would have to estimate it. It's somewhere between 60 and 80, but it's closer to 80 than 60. Again, you would have to estimate that. The green one's right on the line, so that is 60 degrees for your chloroform. So that one is 60. Here you'd have to estimate again. Your diethyl ether is somewhere between 20 and 40, closer to 40, so whatever, 32, whatever you would say for that estimated number. But if you want the normal boiling points, that's what these are. Normal means the boiling point at 1 atmosphere. So your normal boiling point is the boiling point at 1 atmosphere. All right, so your freezing point temperature and your melting point temperature, they are the same temperature. You know water, H2O. If we're going from H2O liquid and we're going to go to H2O solid, that is our freezing point, and this happens at 0 degrees Celsius. If we're looking at H2O solid going to H2O liquid, all right, so now we're melting, and so again, that's at 0 degrees Celsius. So your freezing point and your melting point temperatures are the exact same temperature because you're at equilibrium at that temperature. You will have both the liquid and the solid ice water. So you have ice and water together at 0 degrees Celsius. All right, so here is our diagram. So at minus 20, this is all about water. So at minus 20, this is a temperature versus time. So we're going to pull our ice out of the freezer at minus 20 degrees Celsius. All right, and so it's all ice. And then this ice is going to heat up until it's at 0 degrees Celsius. All right, and so now we're no longer heating it. All right, it is heating up, but the temperature is not changing because the ice is now being converted into water. So right here, it is ice at 0 degrees Celsius. Right here, it is water. This is H2O liquid at 0 degrees Celsius. This is H2O solid at 0 degrees Celsius. And if you're in the middle here, you have ice and water at 0 degrees Celsius. So the far left, that's ice at 0. Far right, that is water at 0. In the middle is ice and water at 0. All of these are the same temperature. So that's a phase change. So we are going to melt our ice here. That's the melting. All right, so then once it's all water, then we're adding heat, and it's going to heat up until it hits 100 degrees Celsius. So right here, at this point here, I have H2O liquid at 100 degrees Celsius. Here I have water and steam at 100 degrees Celsius. And here I have H2O gas or steam at 100 degrees Celsius. All right, so when you start it, it's all H2O liquid at 100. When you end it, at the very end, it is all H2O gas at 100 degrees Celsius. In the middle, you have both water and gas at 100 degrees Celsius. All right, and then you can heat it up even further, and then you are all gas at whatever, up to 140 here they went to at temperature. All right, so you will also see that it takes much longer to vaporize water than it takes to melt water. All right, and so this is called your heat of fusion. All right, it's not called heat of melting, although it's the same thing. It's going to be called heat of fusion. And so you're going to have your delta H of fusion. And this is vaporization, so this is your heat of vaporization. All right, and so that is your delta H VAP, delta H of vaporization. And it's called heat of vaporization because these are endothermic. We have to add heat to the ice to make it into a liquid. We have to add heat to the liquid water in order to vaporize it into a gas. So these are endothermic. As you go to the right, you have to add heat. As you're going to the right, heat is added at a constant rate. If you don't add heat, if you just let it sit there, you're going to end up, after you pull it out of the freezer, you're going to stop right, well, wherever the temperature of the day is. Say in the room it's 20 degrees Celsius. All right, so it's going to stop right there. You have to keep adding heat, all right, until you are at your end of your chart there at 140 degrees Celsius. All right, so the heat of fusion for water, it's a constant. Heat of fusion for every compound is going to be a constant. All right, and so for water, our heat of fusion is 6.01 kilojoules per mole. Heat of vaporization for water, and these numbers will be given, they're not to be memorized. All right, you will be given these numbers. Delta H of vaporization is 40.7. So almost 7 times. So we multiplied this by 7, that would be 42 kilojoules per mole. Not quite 7 times, but about 7 times larger for your vaporization. And if you measured this line versus this line, it would be about 7 times longer, this one, than that one. All right, so it takes about 7 times the energy to vaporize water than it does to melt your ice. All right. All right, so we have we're gonna compare our pressures to our temperature. So this is the Clausius-Clapeyron equation. All right, so this is the Clausius-Clapeyron equation. Again, you're not going to need to memorize this. This equation is given. What you need to know about this equation is this is the natural log button on your calculator. ln is the natural log. You must put this in parentheses because if you don't, it would take the ln of P2 and then it would divide by P1. You have to get the parentheses in here or get your answer for this division, and then you would take the ln of that answer. That's the most common error on your calculator. The other thing that you must have is that your pressure units, they don't have to be millimeters of mercury. They just have to be the same. So these units must be the same. So if you're using millimeters of mercury for P1, then your answer, P2, will be in millimeters of mercury. All right, so they have to have the same pressure units. It makes no difference what the units are, but they have to be the same. Now, temperature is not the case here. You would not want to put in 20. You would not want to put in 34. Notice where your T is at. It is in the denominator. You can never use Celsius if you have a T. If you have a delta T and you're you just know that a change in temperature, again, when we had our delta T, you could use Celsius if it's delta T. Because if you were going from, say, 20 degrees Celsius to 25 degrees Celsius, all right, that is an increase. Your delta T would equal 5 degrees Celsius. It's increasing 5 degrees. But if you change this to 293 and you change this to 298, all right, again, your delta T, it makes no difference. It is 5 Kelvin. All right, so your delta T is the same because you have to add 273 to both of these numbers, and you'll see that your 20 going to 25, well, that's 293 going to 298. That's an increase of 5 degrees, whether you're doing it in Celsius or Kelvin. All right, so, but if you just have T, it has to be in Kelvin every time. There is 0 examples of T that can be in Celsius. No, just T can be in Celsius. Delta T, you can use your Celsius numbers. All right, so you got to add 273.15 here, and so you get 293.2. Add your 273.15 here, and you get They didn't give a decimal for this one for some reason. Well, whatever. You get your 307 Kelvin. All right. So again, these have to be in Kelvin. In Kelvin. All right. Your R value. Again, you're going to be given different R values. The R value has to match the units of your delta H of vaporization. So my R value that I use is 8.314 joules per mole Kelvin. That means that my delta H of vaporization must be in joules per mole. Now note, we just gave the delta H of vaporization for water, it was 40.7. If you put 40.7 in here, you're going to get the wrong answer because it is 40.7. We're doing H2O, which not here. I don't think we're, I have to see, definitely not, because they give us this one. All right, so fine. If you put your 29.2 in here, if you put your 29.2 kilojoules per mole in here, you're going to get the wrong answer because joules do not cancel kilojoules. All right, so you always have to look for your units. They must be exactly the same in order to cancel. And so you will get rid of the K and write times 10 to the third. Now you have joules and you have joules and they will cancel. If you want to convert your R to kilojoules, I don't care. I always convert my delta H of vaporization to joules so that it will cancel with my R value that's in joules. All right, so again, it says here, temperature must be in Kelvin. All right, I don't even write down the number in Celsius. I immediately put it in Kelvin. I do not write this as 34. I immediately put it to Kelvin. And your delta H of vaporization has to be in joules per mole in order to cancel with your R value that also has to be in joules per mole. All right, so again, you're going to have to practice on your calculator by putting these numbers in. All right, so you have your ln, and then you put in your P1. Well, P2 we don't know. P1 is 439.8, and this is in parentheses. Delta H, right? You put your times 10 to the third, so 29.2 times 10 to the third joules per mole. You put in your R, 8.314 joules per mole Kelvin, and your joules per mole cancel the joules per mole. And then you have again in parentheses 1 over your T1, which is 293. And then you're going to, this is where, in minus 1 over 307. All right, so if it is not multiple choice, then you're going to get a lot of credit by just plugging the numbers in correctly. If it is multiple choice and you cannot push the buttons and get the right answer, then you're not going to get any credit. So make sure that you can solve this mathematics equation. So you simply get a number on the right. Make sure you do the parentheses first, then multiply it by the numerator, divide it by the denominator, you get a number. All right, so you will then get your number. All right, and so if you're pushing the buttons on your calculator, you get on the right side a 0.5466. Now you have to get rid of your ln. And so in order to get rid of your ln, you push your second ln or your inverse ln or your e to the x button. All right, and so you're pushing your e to the x button. So ln is base e, log is base 10. All right, so you have your button on your calculator. E to the ln, that just gets rid of your ln. And this on the left is P2 over 439.8 millimeters of mercury. And your E to the 0.5466 is equal to a number that you get on your calculator. And that number is a 1.727. All right, so use your e to the x or your inverse ln. So you should see that that is called e to the x on your calculator. And now, again, to solve for P2, you simply multiply both sides by 439.8 millimeters of mercury. You multiply both sides by 439.8 millimeters of mercury. And then you get your answer in the units of millimeters of mercury. And that is 760 millimeters of mercury. All right, and so our when we had our pressure of 439.8 millimeters of mercury, when we were at 293 Kelvin, when you increase your temperature, we went from 293 to 307, you're going to increase your pressure. So this is a vapor pressure. And so when you are increasing your temperature, you are going to increase your pressure. So make sure when you went from 20, which had 439.8, you're going to 34 degrees Celsius, you know that that pressure is going to increase. So you may not know if it's the right answer, but you will know that it's the right trend, which I had a higher temperature and now I have a higher pressure. And 760 is the correct answer for P2. Note that this is 1 atmosphere. And so that is then the normal pressure. And so this vapor pressure is the normal vapor pressure, and that means that 307 Kelvin is the boiling point of this compound. So your normal boiling point of this compound is 307 Kelvin, or 34 degrees Celsius. All right, so they actually, when they asked the question, what is the vapor pressure at 34 degrees Celsius, that was the actual boiling point of that compound. So when you go back to the question, and it was the diethyl ether. And when we looked on that chart, I'm not sure what I said, I think I said 32, but that was estimated. The actual answer was 34 degrees Celsius is the actual boiling point of ether. And we can prove that by getting our pressure at that temperature. And when the pressure is 760, that confirms that that is the normal boiling point of that compound. All right, we're going to have phase diagrams. All right, far left is going to be your solid, and then in the middle is going to be your liquid, and then the far right is going to be your gas. We're going to have the 1 atmosphere, that's the normal number, is going to be labeled for you. All right, and so when you look at the 1 atmosphere and where it crosses the line between solid and liquid, that is then your normal melting point. All right, so it is melting from a solid to a liquid. All right, so that is your normal melting point. So if you come down and you get that temperature, well, that's 0. So the normal melting point is 0. You keep going. Again, we're at 1 atmosphere, and that's the only time you can call it normal, is at 1 atmosphere. If it's normal, it's 1 atmosphere. All right, and so this is the normal, and now it's liquid to gas boiling point. So here's your normal boiling point, and the normal boiling point is 100 degrees Celsius. So we recognize that, and that's water. So this is your phase diagram for water, because it has a normal melting point at 0 degrees Celsius and a normal boiling point at 100 degrees Celsius. All right, when you are at point A, note that point A touches both the solid, the liquid, and the gas. So point A is called the triple point. All right, so A is the triple point. That means you have equilibrium between solid, liquid, and gas. So any point on the line that separates the solid and the liquid, you have equilibrium between the solid and the liquid. Any point on the line between liquid and gas, that means you have equilibrium between the liquid and the gas. Any point on the line between the solid and the gas, that means you have equilibrium between the solid and the gas. All right, so any point on the line is going to be an equilibrium point. Now, when they meet in the middle here and they are all touching, then you have the triple point, and that's the only spot where it's in equilibrium with the solid, the liquid, and the gas. And that is called your triple point. All right, point C here is called the critical point. All All right, and so we are increasing our temperature. All right, so we are increasing our temperature. And so as you increase the temperature, you're going from a solid to a liquid to a gas. All right, now if we lower the pressure, all right, so we lower the pressure so we can have a high temperature at a low pressure and still we can have a gas the whole time. All right, depending on your pressure units. All right, so the critical point is the point where you only can have a gas. So you have your very high temperature, your very high pressure. All right, and so you have your critical point for this diagram. Let's see what we're going to talk about. Critical point, all right. So the critical point, and that's going to say the temperature of the critical point is T sub C. So when you see T sub C, that means that is the critical point temperature. And so that is the temperature at which the liquid state can no longer exist. And so everything is going to be a gas. All right. There's only one state. All right. Well, it's not called a gas at that point. It's called a supercritical fluid. All right. So we're not going to talk about that, but we're going to only worry about there is a temperature, and it is a very high temperature, and it is the upper right point of your phase diagram, and this is your critical temperature, above which you cannot get a liquid. You have a, I'm not going to even ask the term what it's called above the critical point, but the answer is a supercritical fluid. All right, so your water note, interesting about water, you won't see for many compounds, if any others, and it's the slope of the line going between the solid and the liquid. It is slanted slightly to the left. Every other compound that you will see between the solid and the liquid is going to slant toward the right. All right, so that is a unique thing about water. All right, so here is CO2. What's interesting about CO2 is we have our normal pressure, and we follow our normal pressure across, and it only hits the solid and the gas, and that's at minus 78 degrees Celsius. So note, when you take CO2 and you buy it at the Hy-Vee gas station, it is dry ice. It never will be a liquid. It will simply go to CO2 gas because we are at normal pressure, and so it's only going to go from a solid to a gas. As long as you're above 78 degrees Celsius, it is going to do that. All right. You can get liquid CO2, but you're going to have a higher pressure. And so if you can seal up your CO2 into a container, a very stable container, so that it will not explode because the pressure is going to increase, you will find that you will see liquid CO2 in there. All right, and so you will have, depending on the temperature as well, supercritical temperature is 31 degrees, so at say 20 degrees Celsius here to the left. All right, so if you were at room temperature, although it's going to be colder because dry ice is in there and it is very cold. All right, so you will get a solution of a solution. You're going to get a CO2 that is going to have both solid, liquid in it because the pressure is increasing if you seal it off, and it is subliming. All right, so you can get liquid CO2, but you cannot get liquid CO2 at normal pressures. At normal pressures, at low temperatures, you're a solid, and at any temperature above 78, then you are a gas. All right, in order to get liquid CO2, you have to have a pressure higher than normal 1 atmosphere pressure. Some compounds show more than one type of solid, and here is sulfur, which comes rhombic sulfur and monoclinic sulfur, has 3 triple points. We're not going to do any of those. We're going to stick with the basic solid on the far left, then the liquid, and then on the far right is the gas. All right, surface tension. So water has a very high surface tension, and that's based on all of its hydrogen bonding. And so you will see that you have bugs that will walk right on top of water. You can float a pen right on water, even though the metal of that pen has a higher density than water. If you poke it down, then it will stay at the bottom. But if you put it on there very gently, the surface tension will hold it up. You also, whenever you're reading volumes on your burettes, we haven't done that yet, but and then of course on your graduated cylinders, you have a meniscus, all right, and that's due to the capillary action of your water. And so note that it will have this curve to it. And so when you're reading it, you read the bottom of the meniscus when you have your graduated cylinders, or when we get to our burettes, when we do our burettes, or the pipettes that we did. We wanted the bottom of it to be right on the line. All right, and that is due to the capillary action. Water will always rise up the side and always give this curve to the water anytime that it is in glass. Now, the smaller the diameter of the glass, the more you will find your meniscus. If it's a gigantic beaker, you don't notice it near as much. So this is mercury. So mercury works in the reverse. So if you had mercury in there, all right, so mercury has the reverse look of the meniscus. It doesn't have that capillary action. It's very heavy, and so it doesn't have the capillary action that water has. Viscosity, that is simply resistance to flow. So if you put in, say, a marble and it goes down through water, okay, it will go right through water. Now, glycerol is very thick, or motor oil will be thick, and you stick that in there, and it's going to go much slower to reach the bottom. So that means it is more viscous than, so in this case, the glycerol or the motor oil, if you use motor oil, be more viscous than water. Resistance to flow is your viscosity. We're not going to use this chart. If you need it, it will be given. You should not need that chart. All right, so we're going to talk about intermolecular forces. All right, so we have the van der Waals force. So our intermolecular forces that we talk about are going to be called the van der Waals force, also called, the one that we're talking about here is the London force. All right, all molecules have the London force. So anytime it says give all the intermolecular forces, the London force is the one that all molecules have. It is one of the van der Waals forces that all molecules will have. Now, hydrogen bonding is the other one, but the only molecules that have hydrogen bonding are the ones that have a bond that has an OH in it, or an NH. All right, so there's an infinite number of OH bonds in molecules, infinite number of NH bonds. And then, so these are the two that could be many, many, many different compounds. All right, but I can also put or HF, and there's only one HF molecule. That's it, HF. This is one molecule. So remember, when we did our Lewis structures, that nitrogen will have 3 bonds. All right, and so this could be anything. But if you have NH, you have hydrogen bonding. Remember, oxygen has 2 bonds. Again, that could be anything. So you can have another H here, and that's water, and that has lots of hydrogen bonding. You can put CH3 here, and you've got methanol. That has lots. You can put CH3CH2. You got ethanol, lots of hydrogen bonding. All right, so you're just looking at the OH. If you got OH, you got a hydrogen bond. If you got NH, you have a hydrogen bond. If you have the molecule HF, that also has hydrogen bonding. All right. And so you will then look for whether the molecule is polar or nonpolar. So polar molecule. All right, so when your mu is not 0, you would have a polar molecule, and that would give you a large intermolecular force. And so the way that I always list them are London, then dipole, all right, and then hydrogen bonding. All right, so this is your dipole force. So if you have a dipole force, I think they call it a dipole force, whatever, I just call it dipole force, that means that you have a polar molecule. If you are a polar molecule, which means that your dipole moment is not 0, then you have a dipole. All molecules have London. Now, the larger, more London. So larger molecules have more London. So they're not exactly the same amount of force, but they all have a London force. The larger the molecule, the larger your London force. All right, to have a dipole force must be polar. And if you have hydrogen bonding, right over here, it must contain OH, NH, or HF. Those are the 3 forces that we will talk about. All right, so if we look at pentane versus 2-methylbutane versus 2,2-dimethylpropane, what we're going to find is that a CH bond, remember, a CH bond has a polarity for your carbon is 2.5. That's carbon. Your H is 2.1. So remember, 0.4 difference is considered nonpolar. All right, so any hydrocarbon, that means hydrogen and carbon, and only hydrogen and carbon. All hydrocarbons are nonpolar. All right, and so this one is nonpolar. So this has London, and so that's it. This one has London, and that's it. There's no NH, there's no OH, there's only CH bonds. And this one also has London. All right, so they all 3 only have the London force, one of the van der Waals forces. All right. So then you see which one is larger. Well, they all have 5 carbons. They all have 5 carbons. And they all have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. 12 hydrogens, 3 times 4, 12 hydrogens. They have the exact same molar mass. All right. And so now one's not larger than the other. They are all the same size. And so then you go with a surface area. So this one has a surface area. Let's say we're drawing a straight line. So this one has a surface of 5 carbons in a row. This one only 4 carbons in the row. This one only 3 carbons in a row. And so this one has a larger surface area. All right, and so that means you're going to have more London. And that means you're going to have a higher boiling point. So when you look at the boiling points, they're going to be very similar. This one is 36, this one is 28, and this one is 9.5. All right, and that is all based on the surface area. So this has less surface area, lower boiling point, even less surface area, and even less boiling point. All right, so your London forces, if everything else is exactly the same, then you go to your surface area. And that is simply carbons in a row. 5 carbons in a row, only 4 carbons in a row, 3 carbons in a row. Now you have a branch here to give you 5 carbons and a branch here to give you 5 carbons, but we're looking at carbons connected to carbons in a row without picking up your pencil. 1, 2, 3, 4, 5. This one only 1, 2, 3, 4. This one only 1, 2, 3. All right. To get the other carbons, you have to pick up your pencil and move it somewhere else. All right, so when we look at other molecules, all right, so we have water. Now note, water has OH on both the left and the right, so it has twice as much hydrogen bonding as, say, just an OH. And so it's going to have a higher boiling point than something with just an OH. And we know the boiling point of water, it is 100 degrees Celsius. All right, now glycerol has 3 OH. So this one, I don't know why they didn't highlight that one. This one has 2 OHs. This one would have 3 OHs, so what we would predict is something higher than 100. And so we can't give the actual, but we would say, well, this one has 2 OHs, this one has 3 OHs. 3 OHs is more hydrogen bonding than 2 OHs, and so it's going to have a higher boiling point than water. And this one only has 1 OH, and so we're going to not know the boiling point, but we know it's going to be less than 100. And so here you're going to say less than 100 degrees Celsius. This one you're going to say greater than 100 degrees Celsius. You can't actually give the boiling point, but if they give you 3 boiling points, you can then match them up, because one's going to be 100. You know that one. That's water. One's going to be more than 100. Well, that's the glycerol. One's going to be less than 100. That's your methanol. All right, and so when you draw the hydrogen bonding, what you're drawing is the electron pair to the hydrogen. So remember, when you do your delta plus, all your hydrogens are delta plus, and then remember your electron pair, they're showing it way away from the O, but it's more like right here, and that's where your delta minus is. And so your delta plus, delta minus interaction between the hydrogen of one molecule of water and the electron pair from a separate molecule of water that are interacting. All right, and so for one water molecule, you're going to have 4 hydrogen bonding, because here they're kind of showing it, well, they're not really showing it all 4 of them anywhere, but they're showing the 2 here, but over here you're going to have an oxygen that's going to bond to here, another water, and here you're going to have an oxygen, another water, that's going to interact here. So one water molecule, this one water molecule, and then I'll circle the dotted lines as well. All right, so this one H2O is going to have a hydrogen bond from each of its electron pairs to a hydrogen of a different water molecule, and each of its hydrogen is going to have an electron, is going to have a hydrogen bond interaction to electron pair of another water molecule. So one water molecule has 4 hydrogen bonding interactions. So each of its electron pairs will have a hydrogen bond to an H, and each one of its H's will have a hydrogen bond to an O. And so for one water molecule, it's going to have 4 hydrogen bonding interactions to 4 different water molecules. A different water molecule here for that hydrogen bonding, a different water molecule here, a different water molecule here, a different water molecule here. So 4 water molecules are interacting with the one water molecule in the middle because of the 4 hydrogen bonding interactions. And this has a high boiling point because you have to break all of those interactions in order to vaporize your water. And that is why the vaporization of water has 4 times as high, 7 times higher than your just the melting of the ice, because all of these hydrogen bonding interactions that must be broken. All right, so to see the extent of hydrogen bonding, we can look at our periodic table. And so we can look at the H2O going down the periodic table. Right under O is S, and then right under S is Se, and then right under Se is Te. All right, and so here is the boiling point. So water, we know it's 100, and there it is, 100. Now we do the boiling point of H2S. So we go from 100 degrees Celsius. All right, and so of course sulfur has twice the mass of oxygen. So molar atomic mass of oxygen is 16. For sulfur is 32. All right, and so you're going to have more London forces. It's still polar. All of these are bent. The only thing that the H2S doesn't have that H2O has is hydrogen bonding. And that makes a huge difference, a 160-degree difference. Minus 60 degrees Celsius is the boiling point for H2S. It is a gas at room temperature. All right. And so then when we get down to H2SE, again, higher molar mass, it goes up to minus 40 degrees Celsius. So it has more London. So more London, because it's a higher mass, means it's going to have a higher boiling point. And so minus 40 is higher than minus 60. And then H2TE, TE is even larger. We're going down the periodic table here. OSSETE, down the periodic table. We're getting larger mass. And this one goes up to 0 degrees Celsius for the boiling point of H2TE. And so you can get the extent of the effect for hydrogen bonding. Huge effect. So when if you went backwards, H2TE, H2SE, H2S, you would predict H2O would have a boiling point of minus 80 degrees Celsius. Not even close. It doesn't boil till 100. And that is because of the very, very, very strong hydrogen bonding interactions that water has. Almost any answer, why does water do this, that, or the other? It's because of the hydrogen bonding interactions. They are very strong intermolecular force. All right, we can do the periodic trends for the others. So if we do the halides, so we do HI, and then we do HBr, and then we do HCl, and then we see that HF jumps way up. Again, this has hydrogen bonding. It's the only HF bond that has hydrogen bonding because H has one bond, H and F both have just one bond, and that's it. We don't have more R groups on our F or any other groups on the F. One bond and it's the H, then it has hydrogen bonding. All right, then we go to the next. We go to the nitrogen column, okay, the highest molar mass. It actually, this London force actually overrides the hydrogen bonding of an NH3. All right. So, but when we come down, of course, in molar mass, the boiling point goes down. When we come down further in molar mass, the boiling point goes down. When we go down further in molar mass, the boiling point goes up. All right. So again, the trend should be down, 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 down. It doesn't go down when it goes to NH3 because of hydrogen bonding. We go to the carbon column. So we have our 10. All right, so that's the highest one here, and then it gets lower, and then it gets lower, and then we think, whoa, it's that second row again. It's going to go up. It does not go up. It goes down as you would have maybe predicted prior to knowing hydrogen bonding. All right, what does this prove? Well, this proves that CH bonds do not have hydrogen bonding. All right, and so it's not about being in the second row. It's about being hydrogen bonded. Again, to be hydrogen bonded, HF, or a OH, or an NH. These are the three. All right, the HF, the NH, but not CH. There's no hydrogen bonding here. And so they didn't put the water one, but we saw the water. The water was the huge one. Here, 20 down to minus 90 or so. Okay, so again, that's a 110 degree difference when you do your HF, but not the 160 that the water had. Your NH3 here is call it minus 30 to minus 90. So that's a 60 degree difference. Again, a significant difference, but again, nowhere near the water's 160 difference. All right, so when we're doing intermolecular forces, again, you have London. They all have London. So everything has London forces, all right? Now, if that's all they had, then the one that has the highest molar mass would have the highest London forces. And so in this case, 3 bromines is huge. This is going to have a huge London force here. All right, so oxygen, all right, so you draw the Lewis structure of oxygen, and you see that it is not polar, it doesn't have an OH bond. That's it. O2, London only. When you have hydrogen peroxide, and you draw the Lewis structure, now you see that you have hydrogen bonding. So this has all of them. If you have hydrogen bonding, you have all three interactions. You got a dipole. You can't have hydrogen bonding without a dipole. All right, and then when you have your CHBr3, there is no hydrogen bonding, but this is not symmetrical. You have, again, to draw your structure, and you need to have it in 3 dimensions. Well, the other one I didn't draw in 3 dimensions, but I should have, because this may look like it's symmetrical, but you know that this oxygen has 4 directions, this oxygen has 4 directions, and so your oxygens are all bent. This one is bent, not linear, and that's why it has a dipole. And this one with your H here is not completely symmetrical. And so your delta minus, your delta minus, your delta minus. Now here you don't have a perfect delta minus. So the center of delta minus is not going to be in the middle. It's going to be closer to these 2 bromines over here. All right. So in order for this to be nonpolar, this would have to be a Br. If this was CBr4, well, then it would be nonpolar. All right, but this does have a dipole. All right, so this one only has the London 4s. The H2O2 has all 3, the London, the dipole, and the hydrogen bonding. And this one here has London and the dipole. So you have to be able to still draw your Lewis structures in order to know if you have a polar molecule or not. All right, so then we're going to have different types of solids. That's going to be a molecular solid, a metallic solid, an ionic solid, and a covalent network solid. All right, so these will be multiple choice questions. So you should be familiar with table 11.4 in order to determine what type of molecule you have and then what type of solid that corresponds to. So a molecular solid, so that just means you have a molecule, not an ionic compound. So this is, or an atom. If you have an atom that is a non-metal atom, then you're going to have a molecular solid. A metallic solid, well, that means you have a metal atom. All right, so that one's pretty simple. Metallic is simply a metal atom. Ionic, that means you have an ionic compound. All right, so ionic solids are ionic compounds. A covalent network is going to be one where you don't know what the structure is. All right, so if I give you diamond, all right, maybe you know that diamond's a bunch of carbon, all right, and graphite is also a bunch of carbon. You would not have any idea what asbestos is. So if they give you a name that you cannot draw a chemical formula for, then the answer is going to be a covalent network. All right, so any molecular compound or non-metal atom is going to be a molecular solid. Any metal is going to be a metallic solid. Any ionic compound is going to be an ionic solid. Any name that you cannot draw the structure for is going to be a covalent network. All right, so here's the 3-dimensional structure of diamond. Okay, this is a covalent network, and so here's your graphites. The graphites are sheets of carbon, and here is your tetrahedral carbons for your diamond. Those are just covalent networks. All right, so you also need to know the characteristics. So see your molecular solids here, bunch of molecular solids. And why are they molecular solids? Well, that's a non-metal. All right, that is 2 non-metals together. Here's non-metals together. Here's non-metals together. Here's non-metals together. All right, so non-metals combining together give molecular compounds, and then you make them very cold, and you can make them a solid. In order to make neon a solid, you need to be at minus 249 degrees Celsius. All right, so minus 86. So very low melting points. All right. And so the boiling point's also very low, minus 246, minus 61, 62. Okay, so water is 100 and your acetic acid is 118. But as far as you're going to see the numbers down here, very low boiling point. So if your solid has a low boiling point, there is an excellent chance that you have a molecular solid. So they have low boiling points and also low melting points. But most of the time we talk about a boiling point. Well, not necessarily. Both of them. Low boiling point, low melting point. So yeah, when you're solid, you're going to talk about melting points more than boiling points. So low melting points. When we have metallics, now we're looking for metals. Mercury's a metal, sodium's a metal, tungsten's a metal. All right, so now you're going to have some exceptions to these rules, all right, because you're going to have to say for metallic, it's going to be a variable melting point. Why variable? Well, we look at mercury on the periodic table. It is a different color on the periodic table in the testing room. It is blue because it's a liquid at room temperature. All right, so the melting point there is minus 39, very low. All right, so then we look at sodium. Sodium's a nice soft metal and it has a relatively low melting point, but much higher than the liquid mercury. And then we've got tungsten, an extremely high melting point. And so the only thing you can say about your metals is they have a variable melting point. And here are three examples. One of the lowest melting points, which is mercury. One of the highest melting points, which is tungsten. So it goes from a minus 39 degrees Celsius to 3,410 degrees Celsius. So it is a variable melting point for your metallic solids. Ionic solids, they are all high, 645 up to 2,800. These are high melting points. All right, so again, metal, non-metal, ionic compound, metal, non-metal, ionic compound, metal, non-metal, ionic compound. All right, so ionic compounds have high melting points, also high boiling points. All right, and then you have your covalent network. So it's not going to give you SiO2. It is not going to say carbon. All right, it's going to say quartz. All right. And so quartz is not SiO2. It is many SiO2s connected together. Diamond is not just carbon. It's a bunch of carbons connected together. All right, so it's going to say quartz and it's going to say diamond, right? And so it's not going to say draw the structure of quartz because that would be, well, it's polymer and you would never finish. And same with diamond. It's a bunch of tetrahedral carbons. All right, and so it's just going to say quartz, and you're going to say, what the hell is quartz? I'm like, exactly. So when you don't know what it is, it's a covalent network. All right, so if there is a term here that you don't know what it is, then it's going to be covalent network. If you don't know what cesium chloride is, I'm going to point to the periodic table and tell you that CS is cesium if you don't know what cesium is. Sodium chloride, you all know that one. Magnesium oxide, you all know that one. Tungsten, well, I talk about wolfram, so tungsten, maybe you know that that's an element on the periodic table, but you know sodium, you know mercury. All right, so when you have quartz, you don't know quartz. That is a covalent network. All right, and so your covalent networks have very high melting points. And also very high boiling point. So when you talk about melting point, boiling point, they're going to be the same. They're either going to be low, they're going to be variable, they're going to be high, they're going to be very high. All right, so your molecular solids have low melting points. Metallic solids are variable. Ionics are high, and covalent networks are all very high melting points and boiling points. All right, so here it is in the table. Molecular melting points, low, metallic, variable, ionic is high, some very high, and then covalent networks, very high. A molecular solid, so if you have dry ice, you ever saw dry ice and you throw it on the ground, it will break into 100 pieces. So it is soft and it is brittle. All right, so it is brittle, it breaks into a bunch of pieces. Metallics, variable hardness. So you got your sodium, which is very easy to bend. Then you've got your iron rod that good luck, bending that. All right, so you have variable hardness, and it is malleable and ductile. All right, malleable, you pound it into sheets, sheet metal for all kinds of different things. Ductile means you can put it into wires. All right, so again, conducting, your copper wire is ductile, and it is conducting. Your molecular is non-conducting of electricity. Ionic is hard and brittle, so you got your big things of sodium chloride, big chunks of salt. If you throw a big chunk of salt down, it will break. It is very hard, but it will break. And your sodium chloride and all of your ionic solids are non-conducting solids. However, if you heat it to the liquid state, then it is conducting. So if you heat it up to melt it, then it would be a conducting. But in the actual solid state, it is non-conducting. But if you liquefy it, it would be conducting. Covalent networks, these are very hard and they are usually non-conducting. So if you're looking for a solid that is conducting, if it says that this solid is conducting, well, then you know your answer. It is metallic. Every rest of your solids are generally non-conducting. There may be one or two solids in those things that you could get to be conducting, but in general, they are all non-conducting except for the metallic solids. All right, so now we're going to talk about crystal structures. All right, so you're going to have a crystalline solid. That means it has a perfect three-dimensional structure. All right, so here is copper. So you have coppers on the corners. So these are your corners. All right, so we're going to look at a corner. And this we're going to look at as a face. So we're going to say the corner, note a corner. 1/8 of your sphere is in the corner. So we're looking at how much of this sphere, this atom of copper, is inside of the cube. All right, and if you're on a corner, 1/8 of them, because you can stack 8 dice and they will all touch this corner. So 3 more on the bottom and then 4 on top of it. 1/8 of this sphere is inside of that cube. Now, when we're talking about this one is called a face. All right. And so if you have a dice, you have 6 faces on a dice. In order to cover that one up completely, you just stick a dice right on top of that one. 1/2 of this sphere is inside of that cube. That's the only choices they have for this one. So, okay, then we're going to have others. But anyway, if you're on the corner, 1/8 of your atom is inside of the cube. If you are a face, 1/2 of your atom is inside of the cube. We are only going to be talking about cubic crystal structures. We are not going to talk about any of the other ones. Only a cube. Length, width, height, all the same. That's a cube. So the length times the width times the height, and that is all the same when you are a cube. Length equals width equals height. And so normally we'll say that the edge length is, say, the letter A. And so your volume is simply A times A times A. Length times width times height. If we label it as an A, then the volume of that cube is A cubed. All right, we're not going to do any of the others. We are only doing the cubic crystal lattice. Again, we're not doing any of the others. We don't need to worry about anything else. We are only going to cover the cubic crystal lattice, where your lengths are all the same and your angles are all 90. All right, so the 3 that we're going to cover will be the simple cubic. So you're going to have a simple cubic, you're going to have a body-centered cubic, or you're going to have a face-centered cubic. So it's a multiple choice. It's one of these three. All right, so note when we are a simple cubic structure, we have 4 atoms on the corners on the bottom, and we have 4 atoms on the corners at the top. So we have 8 atoms in corners. All right, but we just stated that only 1/8 of the atom is inside the cube. So inside of this cube, this is 1/8 of the atom, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. And so we have 8 times 1/8, which means that we have 1 atom inside the cube. So here's the cube right here, and there is exactly 1 atom inside of this cube. This is the 1/8 of it, 1/8 of it, 1/8 of it, 1/8 of it. There's 8 1/8 in there. And so that is a total of 1 full atom in the cube. When we look at the body center, again, we have the 8 atoms in the corners, and then we have 1 in the center. So 1 in the center, that entire atom is in the cube. So when you are in the center, the whole thing is in the cube. And so here we have 8 atoms in corners and 1 atom in the center. So with our body centered, we have a total of, well, 1/8, 1/8, 1/8. We have 8 times 1/8, that's 1, plus the 1 that's in the center. So there are 2 atoms in the cube. When we do face-centered, now face-centered has 8 corners. So all 3 of these, there's 8 corners. Now this one has 6 faces. So this one has 8 corners, 6 faces. All right, so a dice, you roll a dice, you get a 1, 2, 3, 4, 5, or 6. There are 6 faces on a dice, and we have an atom on each one of these faces when we have a face-centered cubic. And so when our face-centered, we see that half of the cube is in, half of the sphere is inside the cube at each face. And so we have 6 times 1/2. This is half of the cube inside of the half of the sphere inside of the cube here. That's 1/2 of it. And each corner is 1/8. And so we have 8 times 1/8. And so for this one, we have 4 atoms in the cube. All right, so simple. And then I call that the L number. L is equal to 1. When you are body-centered, L is equal to 2. And when you are face-centered, L is equal to 4, where L is the number of atoms inside of the cube. All right, and so the volume of your cube, which is equal to a to the third, is equal to mammal DNA. So it's easy to remember because it is mammal DNA. All right, so this is the volume of the cube, which we went through. The cube, again, length, width, height, all the same. All right, so your volume of your cube is simply length times width times height, all the same, that we call A. M sub m, this is your molar mass. And that's going to be in grams per mole. The L value, that's the atoms in the cube. All right, so that's either 1, 2, or 3. Simple, body, 4 here, face, 1, 2, or 4. Simple, body, face. That's the only choices for L. It's either a simple, if it's 1, it's simple. If it's body-centered, it's 2. If it's face-centered, it's 4. That's the only choices for L. D is your density, and that is in grams per centimeter cubed. And N sub A is Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. All right, so note that when you're getting your answer here, it is going to be in centimeters cubed. So this is centimeters cubed is your answer. If your density is in centimeters cubed, then your A is in centimeters cubed. And so you're going to get your volume of your cube. That's going to be in centimeters cubed. And so if you take the cube root, you're going to get A in terms of centimeters. All right, so A is going to be in centimeters. It may ask for different units, which it normally does. Normally ask for units of angstroms, and so we will have to do those conversions next time. We will pick up chapter 11 tomorrow.